Welcome to the Explainer. So, to power our modern world, to keep our homes warm and our lives running smoothly, we rely on an incredible, completely hidden world of engineering that most of us will literally never see. When you hear offshore oil and gas, you probably picture those massive steel platforms, right? The ones rising high above the ocean waves. But here's the thing. Not all offshore wells are actually drilled from those fixed platforms or jackup rigs. Out in deeper waters, and honestly, increasingly in shallow waters too, just because the economics make sense, the real magic is happening straight down on the seabed. We're talking about subsea wells. They are the absolute heart of subsea field development.
We are dealing with an environment that is just intensely hostile to human life and mechanical equipment. There's a quote from engineers that sums it up perfectly. All of this is in the dark, at high pressure, often far below any practical diving depth, accessible only by ROV. That really sets the stage for the heroic engineering we're about to look at. Every single valve, every pipe, every sensor has to be built to survive crushing pressures and freezing temperatures, all while working flawlessly for decades.
Here is our roadmap for today. First, subsea wells and trees. Second, building the subsea template. Third, manifolds, collecting the flow. Fourth, the long tieback challenge. And finally, flowline insulation options.
All right, let's jump right into Section 1, subsea wells and trees.
Now, from an installation standpoint, the exact type of subsea wellhead you use is ultimately going to depend on the water depth. But at its core, the wellhead is your crucial mechanical foundation. It is set directly into the seabed. Think of it as this heavy-duty anchor point. The well's internal casing strings actually hang down from it, deep into the earth. It's the structural root of the entire subsea operation.
And sitting right on top of that wellhead is a tight, compact assembly of valves known as the subsea Christmas tree. Now, don't let the festive name fool you. There is nothing simple about this. It's a highly complex, critical piece of heavy machinery. The Christmas tree controls the flow of those extreme high-pressure hydrocarbons erupting out of the well. It's packed with valves. Some are operated remotely from a surface facility using hydraulic fluid, and others are designed to be manually tweaked down in the deep by an ROV, a remotely operated vehicle. This whole assembly basically acts as the heartbeat for a single well.
Moving right along to Section 2, building the subsea template.
So what happens when we go from just a single well to developing a whole multi-well field? Well, the infrastructure scales up dramatically. Instead of a standalone setup, engineers drop down what's called a subsea template. And these things can be absolutely enormous. We're talking massive steel or stainless steel structures weighing up to 800 tons. They are set onto the seabed and have these built-in guide funnels to accommodate 4, 6, 8, or even more well slots, all clustered in one highly organized spot.
This giant steel guide frame does three major things that make or break a project. First, it guides the drilling equipment down to the exact right location with pinpoint precision. You know, when you're dangling tools from a ship thousands of meters above, that kind of physical guidance is totally essential. Second, it gives us a stable, unified structural base for all those individual Christmas trees we talked about to sit on. And third, it integrates seamlessly with our next vital piece of equipment, the subsea manifold.
Which brings us perfectly to Section 3, manifolds, collecting the flow.
At a quick glance, a subsea manifold might actually look a lot like a subsea template, but the big difference is that the manifold structure is purely about the piping itself. The actual Christmas trees might be located around it, sometimes hundreds of meters away. Think of the manifold as the ultimate subsea traffic cop, or a marshalling point. It sits there at a critical intersection on the seabed, grabbing the individual output from all those scattered satellite wells and bringing it together.
So, the manifold collects all that production via these short little connecting pipes we call jumpers. It combines everything into a single, much larger subsea flow line that heads back to the host facility. But wait, it's not just a dumb funnel. It's an active control center. The manifold provides absolutely crucial isolation capabilities. Thanks to its electrically operated solenoid valves, operators way up on the surface can actually shut in or separately test individual wells without having to shut down the entire field. Pretty smart, right?
Now let's tackle Section 4, the long tieback challenge.
The distance between these subsea wells and their host facility, whether that happens to be a fixed platform, a floating vessel, or even an onshore plant, is a huge engineering variable. Short tiebacks of just a couple kilometers, those are relatively a walk in the park. But I want you to really think about this for a second. How far out do you think a subsea well can realistically be from its host platform? Get this, up to 150 kilometers. That is an unbelievable distance.
Trying to push raw, highly volatile well fluids across 150 kilometers of pitch-black, freezing ocean floor creates some seriously epic engineering hurdles.
So let's break down the 3 distinct headaches caused by these massive distances. First up is pressure drop. It's simple physics. The longer the pipe, the more pressure you lose to friction. To push fluids that far, you either need a phenomenally high natural reservoir pressure, or you have to install these complex multi-phase boosting pumps right on the seabed. Second is temperature. Deep ocean water is practically freezing. As the hot well fluid travels, it cools down fast, which brings immense risks of the pipe blocking up. And third is overall flow assurance. You have to stop vaporized gases from creating slugs that choke the flow, and you have to prevent heavy stuff like wax or scale from separating out and gunking up the inside of the pipe.
Let's look at how we solve that temperature problem in Section 5, Flow Line Insulation Options. Before we look at the solutions, we really need to understand the enemy here, hydrates. Under certain cold temperatures and high pressures, water particles actually separate from the gas stream and freeze, and they trap hydrocarbon molecules to form this solid, ice-like substance. That is a hydrate. And it gets worse. Any restrictions in the pipe, like valves or bends, actually create a throttling effect that cools the gas even faster. If engineers don't keep this in check, these solid ice blockages will completely freeze and block the subsea pipeline. And if a blockage forms and then gets violently propelled by gas pressure building up behind it, it can literally act like a missile, smashing right through valve chests and puncturing solid steel.
So to stop hydrates and wax from ever forming, engineers just have to keep the fluid warm. They do use chemical inhibitors like methanol, but heavy-duty physical insulation is absolutely the main line of defense. There are 3 primary options. First, syntactic foam coating. This is a super buoyant composite made of epoxy and glass beads that they spray or mold directly onto the pipe. Second is the pipe-in-pipe method. It's exactly what it sounds like. Your production pipe sits inside a bigger outer pipe, and the gap between them is packed with ultra-high-tech insulation like aerogel or polymer, or sometimes they even circulate hot water through it, like a giant radiator. Finally, wet insulation. This uses incredibly thick layers of polypropylene or polyurethane foam coated right onto the pipe, specifically engineered to withstand direct long-term exposure to deep water.
When you step back and look at it, by combining these massive templates, smart manifolds, pressure boosting pumps, and heavily insulated tiebacks, the offshore industry has essentially built these hidden automated cities down on the seafloor. These systems are designed to just sit there and operate for 20+ years without human intervention. They are pushing the absolute boundaries of what is mechanically possible, miles beneath the waves. It really leaves you wondering, as we discover deepwater fields even further from shore, what crazy, entirely new seabed technologies are engineers going to have to invent next just to bring that energy home?